had a question on the chemical reaction worksheet. What was it again? Lithium?
Sodium hydrogen carbonate.
Sodium hydrogen carbonate.
And then lithium monohydrogen phosphate.
Lithium monohydrogen phosphate. Well, the first thing is we have to get the correct formula. On the test, I'm just going to give you the name. You'll have to get the formula, right? And so if we do, this looks like an AB plus CD, metathesis. So the first thing we do is do metathesis. We form lithium hydrogen carbonate or lithium bicarbonate and sodium monohydrogen phosphate. Now, what happens is, the bicarbonate ion does not dissociate. Bicarbonate, it doesn't dissociate. Why? It's a weak acid. And the same thing with monohydrogen phosphate. That's going to stay together, not dissociate. So one of the mistakes that people do is they break off the hydrogen. You can break off the hydrogens if you're reacting with a base, a base that's strong enough to do that. But in this case, metathesis, we just swap the ions. So it's going to be lithium with bicarbonate and sodium with monohydrogen phosphate. That's what we get. And so do we have a precipitate? No. And so we have no PPT, no gas, and no weaker acid. And therefore, we say that there is going to be no reaction. But this is only for metathesis. What are the two types of reactions that we have to look for? We have to look for redox. So we can look at redox right now. Let's take a look at redox and see. We can start with redox. It's up to you. I mean, this is clearly looking like metathesis, so that's why I started with metathesis. But if we go to redox, we look here, and we inventory. And so what I say here is no reaction for metathesis. That doesn't mean that there's no reaction, because we have to look at redox. So when we look at redox and acid-base, it's kind of nice because they both start the same way. They both start with the inventory. So we'll inventory this. And so sodium bicarbonate consists of sodium ions and bicarbonate ions. Lithium monohydrogen phosphate consists of lithium and monohydrogen phosphate ions, which are HPO42 ions. And then we have one other thing in there. Water. And then we look, are any of these species on there? Yeah, lithium is on there. You should know lithium ion because it's going to be the best or the worst on the chart. Yeah, it's going to be the worst oxidizer on the chart. It's at the bottom. But it's an oxidizer, so we'll just put it there. But it's probably not going to oxidize anything, unless it's something that's really easy to oxidize. We just don't expect it to react. How about sodium? It's bad also. So it's an oxidizer, but so stable. Both of these are very stable. The conjugates are very reactive. So extremely stable lithium ion, very reactive lithium metal. And then we go to bicarbonate, and when we look at bicarbonate, it's not on here. That doesn't mean it can't have redox, right? Because not everything's on this chart. This is not a comprehensive chart of all the redox in the universe. And so what we should do to try to understand the potential redox properties is to do what? What's the first step? If something's not on the chart and you want to analyze its redox properties, what's the first thing you do? Oxidation state. So hydrogen, carbon, oxygen, which one first? And that's +1. And then oxygen at -2. And then finally carbon at +4. Okay, so just analyze this for a moment. What would you call this? Electron rich or electron poor? It's electron poor because of the +4 on carbon. -2 is very happy with oxygen, +1 is fine with hydrogen. This is +4. But if you think about carbon and +4, is it a very good oxidizer? what compound that you can think of with carbon in the +4 that you have direct experience with? CO2. So CO2, we exhale it with every breath. Is CO2 a fairly strong oxidizer? Not at all. I mean, do you have to worry about CO2? Like, you don't want to exhale on anybody because you might oxidize them. Would you? No, you don't even care. You probably exhale on them and not even care at all, right? That you're going to oxidize them, but you might cause other damage. But in this case, we would call this an oxidizer, but not very good oxidizer, right? Could it be a reducer? What's the only thing that can lose electrons here? Oxygen. But do you think oxygen is going to be very happy losing electrons? No, not at all. And so this would be like trying to oxidize water. It's going to be pretty tough. Okay, let's move on to this one. This one's not on the chart either. But let's try to figure out what it's going to be if it were on the chart. And so hydrogen goes first at +1, and then oxygen goes next at -2, which leaves phosphorus at +5. +5 means it's electron rich or electron poor?
It's electron poor.
It's also electron poor. So this should be an oxidizer. But if you think about it, is it going to be a very strong oxidizer? No, not really. I mean, phosphates are used in in some laundry detergents. Some laundry detergents have trisodium phosphate in it, which is just sodium phosphate. But those laundry detergents, you still have to add bleach, if you want, because the sodium phosphate doesn't really have bleaching action, and so and that's because it's not a very good oxidizer. If it were a good oxidizer, it probably should be on this chart because phosphate is very common. Since phosphate is very common, we'd expect it here, like sulfate. Sulfate. And so we would think it's an oxidizer, but not very good oxidizer. So this is kind of the mix, the two-pronged approach. We try to look. We have the numbers here, but we need to place a value on the numbers. I was thinking about this. I was thinking, would you be able to? I was wondering how Chat GTP or version 4 would do, with this, right? What do you think?
Chat GPT or how?
Yeah, I mean, at least for interpreting the numbers, could it do something nuanced like that, or?
Chat GPT doesn't do well with numbers or math, but if it was listed as a word prompt, then it would do much better.
Okay.
Weird as that is.
Well, anyway, this is kind of what we're doing here. Anybody can calculate these numbers. These numbers are very easy to calculate. But the problem is interpreting them. Interpreting them is somewhat nuanced, so it's not so easy to interpret them. And so to make meaning of the numbers is the hard part. But it's an oxidizer. Could it be a reducer? And could phosphorus lose more electrons, or is +5 the max? When you look at the periodic table, it has 15 total. If it loses 5, it goes to neon, which is 10. Are we going to go past neon? No, so this is maxed out. So the only thing that can lose electrons would be oxygen. So we're not going to call it a reducing agent. We're just going to call it an oxidizer. But then this one we do. So technically we should call this one a reducer, but it's just not really going to happen with this one. But water, it's going to be both an oxidizer and reducer. And the oxidizer part is going to be this, hydrogen at +1, and the reducer part is going to be oxygen at -2. It's because of the products it can form. It also depends on how difficult it is to form these kind of things. So if the hydrogens take electrons, and water is not a very good oxidizer, but if the hydrogens do take electrons, we'll make hydrogen gas. And if the oxygens do lose the electrons, we'll form oxygen gas. That can happen. It's probably less likely to happen with these scenarios here. We have to add acid and other stuff, but it's possible. And so, do you think any of these oxidizers will oxidize water? Water is the only real, I guess, reducing agent, unless you want to put these as equivalent to water. Do you think anything's going to happen with redox? No. I mean, it's extremely difficult to oxidize water. None of these are going to be any good at it. Maybe maybe phosphate because it's got the highest charge, but it's also big. You're encountering that. The bigger the atom, the more the charge can disperse within that volume. Oxygen's carbon's a lot smaller than phosphorus. So there are other factors we look at. And so, you know what we predict? We predict no redox. Likely. We would need an extremely powerful oxidizer to oxidize water. And that's the only reducing agent. Okay, so we have no metathesis, no redox, which leaves what? Acid base. There are two acid base reactions that we have to consider. And basically, unless I tell you, we're only going to consider Bronsted for right now, unless I say, this is a Lewis, and then like on that quiz I asked you, this is the Lewis reaction. You can do it that way. But let's take a look at Bronsted acid base and see if we have a potential reaction here. So for Bronsted, sodium ions, are those good proton donors? No. I mean, there's no hydrogen atom, for one thing, and the only protons it would have would be in the nucleus. So it's not going to happen. They're not good proton acceptors. Protons are positively charged. Sodium ions are positively charged. They're going to repel each other. And so what we're going to say is these are neutral towards acids and bases. And then we go to bicarbonate. Now, here, this does have a hydrogen. And so it is potentially a proton donor. And so it could be an acid. And you're going to have this chart, though, here. And once in a while, you should read this chart. The reading is just so you registered it. Because some people, they miss things, like on a test. Like I gave a test, and I had iron 2 on the test. And so people will just go down the list, and then they find, oh, here's iron 2. Right here. And so they called iron 2 an oxidizer. But what they didn't realize that iron 2 is also a reducer. And so I don't know how they missed it, but I do know how they missed it. I never looked at the chart much before, but here's iron 2 on the reducer side. And so once in a while you'll see those, and those will register. Okay, those are both oxidizer and reducer. And so there are other species that are kind of weird too. One of them is like hydrogen peroxide. Everybody thinks that hydrogen peroxide is a good oxidizer. Quite a good oxidizer, but surprisingly, hydrogen peroxide could also act as a reducer. And so that's really weird. This is why there are two waters here. The two waters on the left side are due to hydrogen peroxide, or oxygen, two oxygens here. There's an oxygen here and an oxygen here. The reason why we have the second oxygen here is not because we treat this oxygen as an oxidizer, it's because of hydrogen peroxide acting as a reducer. That's the only reason. Like this one here. And the same thing here. So I don't understand this. Like the final exam for Chem 1A. Did I make the nomenclature separate? I don't think I made the nomenclature separate. But some people get like tunnel vision. And so on the final exam, I had something with fluoride in there. And they wrote F2 minus. They wrote F2 minus, but there's F minus right here on the chart. They could have just seen what the charge is on F. You know, they should have known it anyway. Surprising to write F2 minus for fluoride. But I've seen it a number of times. I don't know where they get the 2 minus from. But once in a while, you want to look at this chart here and then just read these. Perchloric, hydroiodic. You want to name them: hydrobromic, hydrochloric, etc. This one you aren't going to name. This one's Chem 1B. Nitrous, hydrofluoric. Hydrofluoric, surprisingly, is a weak acid, whereas all the other halogens are strong acids.
What do you think that is?
Why it is?
Is it because fluorine so that makes it a weak acid?
No, it's because of the size of fluoride. Fluoride's very small. So the reason is because it doesn't want to break free completely. Fluorine wants all the electrons. And so if we end up firing H plus and fluoride, like this, actually let's draw this, and fluoride, what happens is fluorine's so small, there's still an electrical attraction. And so it's not a covalent bond, it's a positive negative electrical attraction. And what it forms is something called an ion pair, where they just don't completely separate. They're still hanging on, one another. Whereas chloride doesn't have this problem. Chloride can break free. It's just fluoride, because of its size, it sticks on there. And so it requires a second collision. In order for this to happen, to break free, we have to have a second collision, which breaks them apart completely. Because of that second collision, then it's going to be weaker.
Like two magnets.
Yeah, it's like hinder. It should be the strongest,
But because
but there's other factors there. The other factors are how strong the bond is. HI has the weakest bond. That's why it's the strongest. HCl's bond is a lot stronger. So that's why HF is down here. Formic acid, acetic acid, carbonic acid, CO2 and water, hydrogen sulfide or hydrosulfuric acid. When we name H2S as an acid, we call it hydrosulfuric acid. When we name it as just a molecule, we call it hydrogen sulfide. Dihydrogen phosphate, ammonium, hydrocyanic acid, and bicarbonate. And so this is an acid. So you might stop there, but you probably shouldn't stop there, because as we go on the other side here, let's go up carbonate. Oh, here's bicarbonate on the other side. You see it? And so it's both an acid and a base. Then we have lithium ions. Lithium are neither proton donor, proton acceptor, so we call it neutral. And then we're going to have monohydrogen phosphate. Okay, is my chart? No, my chart's okay. Do you see this right here? Mm-hmm. Monohydrogen phosphate.
There are two of them.
Yeah, there's two of them. One on the left, one on the right. And so that means it's both an acid and a base. And then we have water. Water we know is both an acid and base. And so we have three acids. Which of the three is the strongest? So we go back over here and then compare the three acids. And so going down the list, the first one we hit is not dihydrogen. The first one we're going to hit is HCO3 minus, and here is monohydrogen phosphate, and here's water. And so bicarbonate's the strongest of the three. So we'll pick that as our acid. And then we pick the strongest base. So we'll go on the list here, and the strongest base is going to be Monohydrogen phosphate, you see?
Yes.
Monohydrogen phosphate, bicarbonate, and then water's up there, just it's like there. And so monohydrogen phosphate is the strongest acid. Base. Base. Not the acid, base. Strongest base. All right, so now we just react those two. This doesn't mean a reaction is going to happen. We have to have a driving force. But the acid is a proton donor. So if the acid is a proton donor, it's going to lose the hydrogen. And if it loses the hydrogen, what does it make? It's not hydrogen, it's hydrogen ion. It's going to lose H plus, and it's going to make, no. The base is a proton acceptor.
It's going to make carbonic acid, H2CO2.
No, to make carbonic acid, it has to gain a proton. Bases gain a proton, acids lose a proton. This is acid. So it loses a proton, it's going to make what? Carbonate. You can see it here. If bicarbonate loses a proton, we form the conjugate base, CO3 2 minus. So this is going to be the conjugate base, CO3 2 minus. This is a conjugate pair. We can actually look it up at the chart. If HPO4 2 minus is our base, what is the conjugate acid? Yeah, if HPO4 2 minus is our base, then the conjugate acid is dihydrogen phosphate.
Or phosphoric acid.
Not phosphoric acid.
No, phosphoric acid.
That phosphoric acid is 2 steps away. We have to go 1 step. And so if monohydrogen phosphate acts as the base, we form dihydrogen phosphate and stop there.
Oh, okay.
We don't do more than 2 steps. So this will be our conjugate acid. Now we've determined if a driving force is present. So we compare the 2 acids, bicarbonate versus dihydrogen phosphate. And so let's compare the 2 acids, bicarbonate versus dihydrogen phosphate. Which one's stronger?
Bottom one.
No.
Oh, wait, no, we're going out. Casting. Phosphoric acid.
It's dihydrogen.
Dihydrogen phosphate is a better acid than bicarbonate. So dihydrogen phosphate is a stronger acid than bicarbonate. Because of the conjugate relationship, the bases have to hold. That means carbonate must be a stronger base than monohydrogen phosphate. So let's go here. Carbonate must be a stronger base than monohydrogen phosphate, and it is. You see that? So this is a weaker base, this is a stronger base. So the driving force is in which direction? Downhill. This one. So this is a driving force. And so this is what we say. We say there's no
reaction.
metathesis, no redox, and no acid base, Bronsted acid base, and therefore no reaction. We could look for Lewis, but Lewis is like unlikely to happen here in this case. Okay. Were there other questions?
I have another question.
Okay.
Chapter 5, number 78, B.
Chapter 5, number 78B. B. Okay, what type of reaction is this, 78B?
Redox.
Redox. If you look at the type of redox, what types of redox do we have? Element plus element, and then this would be what type of redox? This would be a skeleton redox, right? Oh, O2 minus, there's O2 minus. O2 with a -1 charge is called superoxide. So we have superoxide plus water yields hydroxide plus O2 gas. So the question was how to split it up.
Yeah, I tried a few different ways and none of them were right.
This is kind of weird. Water, usually we don't worry about water. And the same thing with hydroxide. Oftentimes we don't worry about hydroxide too, but in this case, we don't. So you probably want to split this up, like superoxide to oxygen and then water to hydroxide. That's probably the way you want to split it up. But you have to be careful because of disproportionation reactions. Disproportionation reactions, the same species can form two different products, or two different reactants can form the same product. And so this, to me, is looking like a disproportionation. Superoxide goes to hydroxide, and superoxide goes to oxygen. That's what it looks like. Because waters we don't have to really worry about. Water and H+, because those will balance in the end. If there's something missing. So we can just try this and see what happens in this particular instance here. This reaction has to be in basic solution. Do you know why? They didn't have to tell me. They say 78 balance these equations for reaction in basic solution. This has to be in basic solution because hydroxide is present. A has to be in basic solution because we have hydroxide, iron 2 hydroxide. This one can be in either, it looks like, except chromate. The funny thing is, chromate and dichromate are related by pH. So one's more stable in acid solution, the other's more stable in base solution. And D has to be a base solution. So I'm just gonna, once you do enough of these, then we'll just do it here. 2 oxygens means 2 hydroxides. And then 2 hydrogens means 2H+. And then the charge. +2 minus 1 is +1. This is -2. And so we'll need 3 electrons. -3 plus, is that right? Let me see. +2. -3 plus 2 is -1. -1 and -1 is -2, -2. That's it. And so let's check the balance. 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. And the charge, -3 plus -1, -2. Yeah, -2. Okay, then let's go over here. The oxygens are balanced, we just need to balance the charge. And so we just need 1 electron over there. So that was easy, that particular one. And then what we do here is just multiply, looks like this one by 3. Yeah, 3, 3, 3. Then add them up. Electrons should cancel. Electrons always must cancel. If you have electrons left over, either on the left or the right, something went wrong. You got to start over again. And so the electrons cancel. We can go ahead and cancel those. And then we'll add everything out. 2H plus a superoxide plus 3 more superoxides yields 2 hydroxides plus 3 O2s. And so let's combine the superoxides here. 2H plus 4 superoxides. Now, this is what we mean by disproportionation. Disproportionation means the same substance, superoxide, acts both as the oxidizer and the reducer. And so what that means is, well, how can they? Well, they don't. If I have 4 superoxides, 3 of them will act as the reducer. Reducing agents will lose electrons. 1 of them will act as the oxidizer. And so this one here is going to be pegged as the oxidizer with H+. These 3 are going to be the reducer, but it's the same species, but not the same. superoxide. One of the four has to be the oxidizer, the other three are the reducer. Well, altogether we have four of them, so now we just call it both. This is both the oxidizer and the reducer. If I combine them like this, that's going to lead to 2 hydroxides plus 3 oxygen. There is a driving force for this. And so we use the conjugate relationship here to figure it. So if this is our oxidizer in the forward direction, then this will be our reducer in the reverse, the conjugate. If this is our reducer in the forward, then this will be our oxidizer in the reverse. So what we're going to have here is this. Probably we might leave it in this form here. The hydroxide will be our reducer, and the oxygen will be our oxidizer. So we're going from stronger to weaker. Stronger to weaker is driving force, and we know the driving force is present, otherwise they wouldn't have got those products. So this has got to go from stronger to weaker. So what that means is that superoxide is a stronger oxidizer than oxygen gas. Oxygen gas is already a great oxidizer, but superoxide is even better. But oddly enough, superoxide is a better reducer than hydroxide. Hydroxide is not a great reducer. But superoxide is due to the instability. It can be. Does that answer the question? So this is one of those disproportionation, and then water will throw you off for that. In fact, oftentimes they just ignore the water. Sometimes they'll just go to blank, like D. If you look at D, silver and cyanide is going to go to this here. But oxygen, you can eliminate hydroxide too, but oxygen goes to blank. In this case, oxygen goes to water, or oxygen and hydroxide go to water, which is fine. But the problem is this is in basic solution. I shouldn't have stopped here because is H plus stable in base? No. And so what I need to do is I need to neutralize the acid. And so how do I do that?
Add 2 hydroxides.
Yeah. I need to add 2 hydroxides here. And to keep things balanced, I have to add them to both sides. Otherwise, I just screwed up the balance. And so if I have 2 H plus and 2 hydroxides, how many waters do I have? 2. 2 H2O liquids plus 4 superoxides. It's going to yield 4 hydroxides plus 3 oxygens. Okay, and that would be it in basic solution. Were there other questions? No. All right, I had some questions about the exam 1. I decided I'm going to just post the key for exam 1 since I don't have enough time to go through it. So, and then I did post did you guys see on Canvas, I did post the old exam 2?
Yes.
Okay, good. The exam 2 next week is looking to be chapters 4, 5, and 6. I probably won't put any chapter 7 on that. It's just 4, 5, and 6. Okay, so we talked about manometer and simple gas law. Probably the biggest simple gas law. Actually, there are 2 simple gas laws you probably should be aware of. One is Charles' law. Why? Why bother remembering Charles' law? Yeah, volume and temperature.
It proves absolute zero.
Yeah, it just predicted absolute zero would come out minus 273.15 Kelvin. So Charles was important. What was the other one? Not Dalton's. Dalton's is important, but Dalton's is not one of the simple gas. Dalton's for gas mixtures, some of the partial pressures. That's one you should know. But it's the companion to Dalton's, which is Avogadro's.
I was going to say combining gas law, but my thinking
So, yeah, we'll talk. The combined gas law is the one you want to remember. And so if we throw in Avogadro's in there, we're going to get P1V1 over N1T1 is equal to P2V2 over N2T2. And so this is the combined gas law. Most of the combined gas law problems are fairly straightforward. The only thing in Chem 1A, this is something, in Chem 4, the number of moles never changed, right? And so in Chem 4, it was P1V1 over T1. You remember that? Yeah. Is equal to P2V2 over T2. In Chem 1A, sometimes something leaks out, some gas leaks out of the container. If some gas leaks out of the container, then the number of moles change. Or sometimes you force more gas into the container. And so if you force more gas, then the number of moles change. That's going to change the pressure or the volume or whatever. We'll end up changing those. And so that's one of the differences here. We have something with pressure. I need to talk one more thing about pressure. Let's see. The manometer reads the absolute pressure, but some instruments don't read the absolute pressure. Some instruments measure PSIG versus PSIA. Do you recall the difference between PSIG and PSIA?
PSIA is 14 point, or whatever the pressure is of the air less than PSIA or PSIG.
Yeah, pretty much. They differ in the zero. So 0 PSIA is absolute zero. There's no gas present. Whereas 0 PSIG has a different meaning. Let's say you go out and buy a helium tank. Although I guess helium is getting really hard to. Yeah, hydrogen instead. So you're filling up helium balloons and the tank goes empty and you can't fill up any more balloons. Is the tank really empty? It turns out, no, there's still some helium left in the tank. How can you get it out? Well, you have to suck it out. Can you suck it out? Yeah, you could. You could suck it out. Could you suck out all of it?
No.
In theory, you could. In theory, you could suck out all of it. But, let's say if you did suck it all out, you know what's going to happen to the tank? It's going to get crushed.
Mm-hmm.
It's going to get crushed because we live in the bottom of the ocean. And this ocean's the atmosphere. And it weighs, how much does it weigh? It weighs 14.7 pounds per square inch. And so it depends on how strong the helium tank is. If it's a big, heavy cylinder, it's not going to get crushed. But if it's one of those thin, flimsy tanks, it's probably going to get crushed or at least partially collapse. So when you have a gauge on your helium tank,
Just a question about the ideal gas law. For R, what units are standard for this class? Or what values are?
Okay, I only memorized one.
I know 30 point or 8.31, but
You know 0.08206?
but that's what I'm guessing.
Yeah, I only memorized one. Chem 4 is ridiculous. In Chem 4, he loves you to memorize a whole bunch. 66.4, 0.821. Do you remember those? He wants you to measure a whole, to memorize a whole bunch, but it's not really worth it because you have to memorize the conversion factors anyway. So why bother? And so I'll tell you what I have memorized, and then we'll see. If you work with compressed gases, you never let it go to 0 psi G. When you buy compressed gases, if you let it go to 0 psi G, then what can happen is air can leak in and other gases can leak out. So we buy ultra pure helium. You buy ultra pure helium and you let it go to 0, they're going to charge you extra when you return it. The reason they're going to charge you extra is because they can't just refill it. They don't know if air got in there. If air diffused in there, then what they have to do is they have to suck it out. And the problem is they don't have vacuum pumps strong enough to suck everything out. So they have to do what's called like a purge, refill, purge, refill, purge, refill cycle over and over again, like we did. Remember when we had to rinse the water out of the burettes and the pipette and whatever? You know, we did multiple rinses. Well, they have to do the same thing. They have to do multiple rinses with gas. And it's expensive gas because they have to rinse this with ultra pure helium. And so it's going to cost you a lot more money. And so whenever we returned a cylinder, it was always with like 5 psi left. You know, we'd have like 2,000 psi to begin with, over 2,000 psi G to begin with. And we'd let it go to about 5 psi G and then return it. And they're thinking, it's a little bit of money, but it is a little bit of money, but it's a lot of money if they have to rinse and purge. And it's rinsing with gases. If they could suck it out, if they had a vacuum pump, they could just pump out this to perfect vacuum. Perfect vacuum has no air in there. And so PSIG is a relative scale. It's, it's when it goes empty. It's the same as atmospheric. And so if atmospheric pressure is 1 atmosphere, 14.7 psi, then when the tank gets to 14.7 psi, then they're equal opposite. And so you have 14.7 psi pushing out, 14.7 psi pushing in, you're going to have a tie. So we need an overpressure in here. That's why you keep the 5 psi. So technically, 0 psi G is equal to the barometric pressure, whatever the barometric pressure is. We'll just take it as normal barometric pressure. Because that's when you open the tank and nothing comes out, that's got to be equal to normal barometric pressure. And so we'll just assume for right now it's normal. If it's normal, then what the gauge is going to read when we hit 0 here, it's going to read minus 14.7 psi G. And so that's called minus 14.7 psi vacuum. And so vacuum is just lower than normal atmospheric pressure. So when I have minus 14.7 psi vacuum or 0 psi A, there's no gas in there. It's empty. There's no collisions. And so this is some tank here. There aren't too many PSIG type problems in this book here, but it's important to know. So in this, it doesn't matter what units we use. We could use any pressure unit, torr, millimeters, whatever pressure unit we want. We can use any volume of the unit, milliliters. But we can't use any temperature unit. Temperature has to be Kelvin because the 0 is an arbitrary 0. If you put 0 under here, you're going to get undefined. And so it has to be absolute Kelvin. It's the same thing here. 0 psi, it's still got pressure. It's still got 14.7 pounds of pressure there. And so temperature has to be absolute. Now, for the ideal gas law, PV equals nRT, I try to minimize the amount of memorization I have to do. In order to minimize the amount of memorization, I want the units for pressure to be in what? Atmospheres. And volume, I want it to be in liters. N should be in
Moles.
moles, and T should be in Kelvin. And therefore, I'm only going to memorize one R. And the one R is 0.08206 liters times atmosphere per mole Kelvin. This is what I memorized here.
Do we need to go any more specific than 4 significant figures?
No, just the 4 sig figs is plenty. But there's a problem because atmospheres is not the SI unit. Actually, what is the SI unit?
It's either bar.
SI unit is not bar.
Is it not bar?
It's not bar.
It's not bar.
SI unit
It's
is
not bar.
pascals, which is kind of the same thing as bar, but not exactly. Although the SI unit, I think the SI unit is Pascal. But what is the standard pressure now? The standard pressure is not in atmospheres anymore. The standard pressure is in bar. And so this is what I memorized. If I have bar, let's say, and I have the pressure in bar, I have to convert it into atmosphere. So I need to know the conversion. You don't have to memorize this one. This one we get in. Given that there is 1.01325 bar per atmosphere, for 1 atmosphere. This is exact. So this is the only reason I memorized the 6 figs because then it's exact. I don't have to worry about round off error. But I have it memorized. I have, and then the conversion for pascals and that kind of stuff, you don't have to have memorized. So you're going to be given that. And then our standard conversion factors will minimize. And so you have to memorize this. There's another value for R. The other value of R, I don't necessarily have to memorize. You can memorize it as well. Maybe it's easier to memorize. I memorized something else, which we're going to talk about later. If I know this, how much work does it take to blow up a balloon? What are the things that, if you think about it, what are the things that will dictate how much work it takes to blow up a balloon? Well, one thing is, how big of a balloon do you want to blow up? The bigger the balloon, the more work. Right? What else? There's one more thing that dictates how much work it takes to blow up a balloon.
Elasticity.
Yeah, we'll ignore the elasticity because that's
Like that has to do with volume.
How about the strength of your lungs?
I was gonna say lung capacity.
right. Well,
Good knowledge.
you're using a machine, so,
Okay. Okay.
so you don't have to do the work. You just have to push the button and then.
The force of the pressure.
It depends on where you blow it up. Like, if you blew up a balloon on the moon, it'd be a lot easier than blowing up a balloon on Earth. Why?
Gravity.
Because the air pressure on the outside of the balloon.
Yeah, the air pressure on the outside of the balloon. I mean, there's very little atmosphere. If you blew up a balloon underwater, I don't know if you tried it, but would it be easier or harder? Yeah, and the deeper you go underwater, yeah, it'll be harder to blow up the balloon because you got more pressure on it. And so that's work. And so there's one thing. Did you know we can calculate it? It turns out it takes 101.3 joules of work to blow up a balloon, 1 liter in size. And so it takes this much work to blow up a balloon, 1 liter in size, under normal atmospheric conditions. And so 101.3 joules per liter atmosphere. Okay, so if you know this, This is called pressure volume work. Yeah. PV work. Then we can do a conversion. Do you see liters atmosphere here? Liters atmosphere, that's the same as work, you know? And so what we can do is we can do this. R is equal to 0.08206 liters times atmosphere per mole times Kelvin. And then we use this conversion factor, 101.3 joules per liter atmosphere. And then the liters in atmosphere cancel liters in atmosphere, and that leaves us with joules per mole Kelvin. And so what does that come out to?
Like 8.31.
Yeah. This comes out to 8.314. You just need to know it there. Joules per mole Kelvin. So technically, I mean, you don't have to have this memorized if you know this one. But either way, the other way you can get how much, if you forget this one, and you know that one, then this one's easy to derive because this one is just equal to 8.314 joules per mole Kelvin divided by 0.08206 liters atmospheric per mole Kelvin. And so this is what you try to do. You try to minimize the amount of memorization. You try to minimize the amount of memorization by coming up with these relationships like this. So moles Kelvin cancel, that leaves me with joules per liter atmosphere. Joules per liter atmosphere comes out to 101.3. And so memorize one and derive the other. Most people memorize this one, and therefore they can always derive how much work it takes to blow a 1 liter balloon under normal atmospheric pressure. 101 joules. If you're ever curious, you know, about how much work you have to do. Otherwise, there's not that much memorization. You know, the combined gas law, the ideal gas law are. And so I just memorized these. Applications of ideal gas. Ideal gas applications are pretty straightforward. You know, we have 1, 2, 3, 4, 5 things. If we're given 4 out of the 5, then we can calculate the fifth just using algebra. And so that's it. And so most of the calculations are pretty straightforward. So one is just solve for the variable. Given the others. The second application is this. The second application is the, actually I don't know if I'm going to go in order here. I'm going to go in order of how much you use it. And so the next most important application I think is molar volume. I use that a lot. More. Molar volume is how many liters per mole. So it's V over N. How many liters per mole? Do you know what V over N is equal to? Algebraically? So we're going to get V divided by N is equal to RT divided by P. RT divided by P. So how much space a mole of gas occupies depends on the temperature and the pressure. The higher the temperature, the bigger the volume or the smaller the volume? Yeah, the higher the temperature, the bigger the volume. The higher the pressure, the smaller the volume. So increasing T increases the volume, increasing P decreases the volume.
Bless you.
And so we can calculate the molar volume. Now, one thing we want to know is, what is the molar volume of gas under normal conditions? What are normal conditions? 25 degrees C and 1 atmosphere. And so let's do that. At 25 degrees Celsius and 1 atmosphere. Well, what is the molar volume? The molar volume, I'm just going to call NV, which is equal to V over N, which is equal to R, which is going to be 0.08206 liters times atmosphere divided by mole Kelvin times T. T is going to be 298.15 Kelvin divided by P, which is just going to be, let's say, exactly 1 atmosphere. And so what does that come out to? I actually have it memorized, but I don't have it memorized to that many sig figs. So let's get it to more sig figs. 0.8026206 times 298.15. And I get, 24.466. How many sig figs are allowed? 24.46 liters per mole. That's what the units will work out to. Atmospheres canceled. It gives us liters per mole. Okay, to 4 sig figs, what would it be?
24.47.
24.47. I usually memorize it to not 4 sig figs. I usually just memorize it to 3 sig figs. Yeah, it's because it's an easier number to remember, the 3 sig figs. So I have this memorized to 3 sig figs. 24.5 liters per mole. This is for any gas. And so about 24.5 liters per mole at standard ambient conditions. I shouldn't call it standard. I should just call it RT and RP. You know what RT stands for?
Regular temperature.
Regular temperature or room temperature, and RP? Room pressure.
Room temperature was 67. Our heat is not like this today.
It's pretty cold.
Which is great. My room is normally very hot in terms of temperature to the rest of my house.
This is a really useful number here to know.
It's not the brain.
What if I didn't want it in atmospheres?
Converted.
I'd have to convert it to bar.
Very too bad.
Do you know how I'd convert it to bar?
By using our handy dandy conversion.
Yeah.
1 atmosphere is equal to 1.01325 bar.
And so if I wanted it in bar, I would have done this. I would have converted my pressure, 1 atmosphere, into bar. And so that would have meant I would have done this. If I need this in bar, I would have done 101.325 bar per atmosphere down here. So if I take this number and divide it by 101.325, then I should get it in bar. A bar is a little bit smaller than an atmosphere because it takes more bar to make an atmosphere. And so it's a lower pressure. Lower pressure means the volume is going to increase. It's not going to increase by much. It's going to increase by a little bit. So let's see how much it increases by. So I'm going to divide by 101.325. Did I get that right?
I'll just say,
No, like you need to
The R
put
value.
one bar and then
Oh, I need to change my R, right. Oops, sorry. Let's do that. Here, I'm in atmosphere, so I need to divide it by, I need to multiply it, right? Because I need to cancel out atmosphere. So 1 atmosphere is equivalent to 101,325 bar. So I made a mistake here, but now this should be right. Atmospheres will cancel atmospheres, leaving me with bar. Okay, so I shouldn't have divided. I should have multiplied by 1.01325. See if I can square that. Times 101,325. Now this makes sense. It should be bigger.
Which is less than 1 atmosphere. So you should have like 999. Might be the same thing.
Oh, yeah, because it's two in the same.
Okay, so it's 24.5 liters per mole at RT and RP. Room pressure is 1 atmosphere. Room pressure is 1 atmosphere. It's 24.8 liters per mole at RT and 1 bar. 1 bar is a little bit smaller pressure than normal atmospheric pressure, and therefore the volume is a little bit bigger, 0.3 liters bigger, or 300 milliliters bigger. And so normally what I do is I know this one. I don't remember this one. If I need it, I'll calculate it. But, maybe it's not so difficult to memorize. The one I think I finally, the one I had memorized for many, many years is the molar volume at STP. You know the molar volume at STP? Did you guys memorize that? You didn't memorize it?
this is 22.1.
Close. Maybe I forgot it. No, it's 22.99. Is it 22? I don't think it's 22.7. I think
I was thinking at 22.7, but then
Oh, is it? Maybe it is 22.7.
22.68.
I thought it was 22.3 or 22.4.
22.682.
What's the only significant figures?
No, I had to memorize this.
What do you think?
But,
22.4.
yeah. I had this memorized for many, many years.
I don't know, 6.02 times 1 because they don't want to put the caret.
I had to memorize this.
1023 times 1023. No, definitely not.
And I thought I'd use it. If you have to memorize it, you think you'd use it. I never used it. Only time I used it was to answer test questions. But I actually never used it. So I thought, wow, what a waste. I spent all that time memorizing it and then never benefited from it. But you might have a test question, not from me, but if you take a standardized test, I might ask you. But it's easy to calculate because this 22.4 liters is the molar volume at STP. STP stands for standard temperature. And what is standard temperature? 0 degrees Celsius. And standard pressure. Now, standard pressure depends. This is why I get it mixed up because they switched it. It used to be standard pressure was 1 atmosphere. And so is this standard pressure 1 atmosphere or is this standard pressure 1 bar?
Atmosphere.
And so this is,
Find out.
let's see.
So 64.
I'm saying
They changed it
that's
again.
the one now.
This is this is for atmosphere. So if I need to do this in bar is a little bit smaller, and therefore it's going to be a little bit bigger. And so if it's a little bit bigger, it's going to be 101,325 times bigger. So times 1.01325, and it's 25.11, or 25.11 liters per mole at STP, in which the pressure is bar. This is STP with the pressure of the atmosphere.
So that's 22.4 times 1.01325 bar.
Yeah, per atmosphere.
22.69.
Oh, did you get 20? Yeah, maybe mine's way off.
I would say it's added an additional 3.
Yeah, 3 liters. That's wrong. 22.69?
Yeah,
We'll just do-
22.69.
We'll do 22.7. Do you want to memorize any of those?
No.
Yeah, it's a lot of work to memorize those, and you're not going to use it. You're not going to use it unless you work at 0 degrees C. Now, the funny thing is the mercury barometer, you would think they would calibrate the scale, because do you know that like water expands with temperature? This is why the density goes down.
So does mercury.
And so does mercury. Mercury is another liquid. It expands with temperature and contracts. If you increase the temperature, it expands. If you decrease the temperature, it contracts. Most of the time, we don't care about that, but it makes a difference. Like, I was watching this thing on TV about the Concorde, the supersonic jet. We want to bring back supersonic jets. They're talking about how much the metal expands, during flight because it gets so hot. And it expands so much, it's a little bit scary because you're thinking, wow, hopefully the engineering is really good because you don't want it to fail. But anyway, so metals expand and contract more significantly with temperature than water. And so it turns out that, well, if they're going to pick a temperature, they have probably 2 good choices. One is 0 degrees, and the other would be 25 degrees. Which one did they choose? They chose 0 degrees. So they calibrated at 0 degrees. And therefore, it's a good idea because, you know why? Because the correction's always the same. If they figured nobody's going to work under 0 degrees, right? Unless it's outside. If the barometer's outside, then it might be under 0 degrees C. So they figured it. Therefore, each time you correct it, it's going to be a subtraction. Versus if they pick 25, then above 25, it's going to be a subtraction. Below 25, it's going to be an addition. So they don't want to mix things up. And so they calibrate it low, and then it's always the same. It's like Celsius and Kelvin. It's always add 273 or subtract 273. It's simple, But you don't want to flip the equation. And so they chose 0 degrees C. So that's why on the report sheet it asks you for the mercury expansion correction. And the mercury expansion correction's in there, but we're not going to use it because we didn't use a mercury barometer. We used a digital barometer, which has a different kind of sensor. The digital sensors measure a lot of them, the ones I used to use for pressure, measure the thermal conductivity. Like a vacuum thermos, and if you have a perfect vacuum thermos, then your coffee should stay hot forever because there's nothing to conduct the heat away. But it's not a perfect vacuum thermos. It's a pretty good vacuum thermos, right? So what happens is you have a hot inner surface, and the hot inner surface is vibrating like this. And it wants to transfer the kinetic energy to the air. And if there's a little bit of air, it can transfer that kinetic energy to the air that's still inside the vacuum jacket. And then it can transfer that kinetic energy to the outside wall and then dissipate it to the surroundings. But if you had a perfect vacuum thermos, it would be a perfect insulator, thermal insulator. And so these gauges just measure the thermal conductivity between 2 probes, how much, and then you can figure out. Okay. So, again, you do not have to worry about what is the mercury calibration and uncorrected versus corrected. You know, we just use a digital gauge to measure the barometric pressure yesterday. And so you have the absolute pressure. We don't have to do anything. The absolute pressure was 30. Oh, well, you do have to do something. You have to convert it from inches to millimeters.
What's the Lusak's law?
Gay-Lussac's law?
Yeah, give me.
Gay-Lussac's law. Let's take a look at Gay-Lussac. Gay-Lussac's law is volume, and it's like Avogadro's law.
Volume is proportional to moles.
Yeah, basically that.
Oh,
So sometimes it's called Avogadro's / Gay-Lussac's law. In our book, they say we're going to do it wrong. Boyle's law, pressure and volume. Charles' law, volume and temperature. Dalton's is, gas mixture, and Avogadro's can be gas mixtures or pure.
And there's the combined gas law.
Or the combined gas law. Yeah. What is this? Socratic.
Yeah.
now we're touchboard.com.
So molar volume is important, and the molar volume for this is pretty useful to know for chapter 7. We're going to be using that because we're going to have to calculate how much energy it's going to take to blow up balloons. It's a pretty simple calculation, but we want to be able to calculate the volume changes quite quickly. The other application for this is density. This is pretty useful too. Like, what is the density of air? We can measure it, but why measure it if you can just go ahead and calculate it? It's such a simple calculation. The density of air is equal to the mass divided by the volume. But the problem is well, then we have to measure the mass and measure the volume, so it looks like we have to calculate it, but we don't have to calculate it. You know how we can avoid calculating it? We could use the molar mass, right? And so what we're going to do is this. We know that the volume is equal to what? We know that the volume is equal to nRT over P. And then we'll substitute that in here. And so this is going to be the mass over nRT over P, and then invert and multiply. So we're going to get the mass times P divided by nRT. But when we look at M over N, M is in grams, N is in moles. That's grams per mole, that's molar mass. And so this is equal to, the density is equal to the molar mass. The molar mass, you can use different symbols. Like the symbol that we saw in the previous chapter was like this, with the M's would splayed out like that. What does our book use? Our book uses different symbols for molar mass.
I wouldn't be surprised if it's just a lowercase m.
So this is 6.4. This is 6.4.
I thought that was molarity for
Oh,
the
you know
meters
what?
of meters of mole.
You might be right.
Or moles per liter.
Molarity is vertical.
Yeah, molarity was the uppercase, moles was lowercase.
No, this is not molarity. This funny M.
That's funny.
And that's molar mass.
This is molar mass.
Capital M is molar mass?
Well,
Is that right?
okay, the difference between molarity and molar mass is this. This is molarity.
Uh-huh.
This is molar mass. Do you see it?
No.
Yep, I do.
Okay, this is molarity. And this would be molar mass.
Italics or strings.
That's
don't know what you call that. This is funny looking at.
The skinny M and the wide M.
Yeah. Okay, let's go with that.
I think they're using italics to differentiate.
Yeah.
It's the way of writing.
Okay, italics, that's good.
Which one's italics?
The one that's curved, the one that's tilted.
So we end up with this equation.
The
So I'm
wide
gonna
one?
make this, whatever, like that. That's mole mass
Okay.
times pressure, P, divided by RT. So we can get the density of any gas as long as we know the molar mass. Do you recall the molar mass of air? The effective molar mass of air? Somebody remember the number? Just to maybe 2 or 3 sig figs.
28.97.
Okay, good. 28.97. You know, or roughly what? You know, to 2 sig figs it'd be easier to remember. What is it?
2.9.
29. Nitrogen's 28, oxygen's 32. There's more nitrogen in air, so it's closer to 28 than 32, so 29 it is. But anyway, we can get it to more sig figs. The density of air is going to be 28.97 grams per mole times the pressure. Now, I only memorize 1 R, so the pressure I'm always going to have is 1 atmosphere. If I need to change it, I'll change my R. The R is going to be here 0.08206 liters times atmosphere per mole Kelvin. So let's say I'm given bar. Here, I'll just change my R by changing atmospheres to bar. That works. Times the temperature. The temperature, let's do 298 Kelvin. 298 Kelvin room temperature. Usually I don't use the 0.15 most of the time. Just go with 3 sig figs. But you can do it 298.15 or 298.2. Maybe we should do it. Because I have 4 sig figs, I'll just do 298.15. So this is going to give me 28.97 divided by 0.08206 divided by 298.15 gives me 1.1840. How many sig figs am I allowed? It looks like 4. And what are the units? Grams per liter. So 1.18 grams per liter. Actually, a lot of people have it memorized. 1.18 grams per liter. But I don't have it memorized. Well, I did have it memorized. Well, we can calculate the density. What's the density of helium? Helium is about, helium's 4 grams per mole. Right? And so the density is going to be a lot less. In fact, it's going to be 4 times what? 4 goes into 28 how many times? 7 times? It would be like 1/7 the density. Something like that, yeah. Helium. And so we can calculate what is the density of oxygen gas at 290 Kelvin, 0.987 bar. Here, I don't memorize this R. Do you see this R? Yeah, I just convert atmospheres to bar. And I memorize the 101.325. But you don't have to memorize that either.
I'll say density of helium is like 0.4.
Yeah. There's one other application for this, and it depends on how precisely you can measure the density of a gas. If you can measure, let's say you purify gas and you measure the density very precisely with a lot of sig figs, then you can use the density to calculate the unknown molar mass of a gas. This gives us another way, to determine molar masses. How are molar masses typically determined? They're typically determined using like a mass spectrometer. You just weigh the molecules. But if you don't have a mass spectrometer, then you can do it the cheap way. The cheap way is to measure the density of the gas and then determine the molar mass. Well, that gives us the next application. The next application is, let's say I want to do it the cheap way. I don't want to invest in a mass spectrometer, and I want to be able to figure out the molar mass of a gas. How can I do it? And so the molar mass of a gas, is equal to the mass over moles. And so we do the same thing. We know that N is equal to, what is N equal to? N is equal to PV over RT. Right? And then we'll substitute that in here. So that gives us the mass over PV over RT. Then we'll invert and multiply. So the molar mass of the gas is equal to MRT over PV. Well, the mass divided by the volume is equal to the density. So let me make sure I'm using the right symbol for density. Are they using D? Because there's another common symbol, rho. They're using D. I'm going to use D. Is equal to dRT over P. So if we can do very precise density measurements, then we can calculate the molar mass or experimentally determine the molar mass. And then we could use that to convert the empirical formula to the molecular formula for gases cheaply. But maybe not with the precision of a mass spectrometer. The precision of a mass spectrometer is huge. Yeah, it's very precise. So that's the other application. So those are common applications.
Is it just the?
Yeah. Now, or is it 4 or 3?
It's 4.
It's 4.
4. Right, I got this stuff.
Very small.
Solve for barriers, molar volume.
Density, and molar mass of gas.
This should be 3. This should be 4. Yeah, just those 4. Now, the next thing is gas stoichiometry. And so this is why I like to memorize the molar volume under normal conditions. When we do chemical reactions, under what conditions do we normally do chemical reactions? So if we mix things together, we normally do it under room temperature and standard pressure, which is 1 atmosphere. And so this is why I have it memorized. I have it memorized at 24.5 liters per mole, but that's only 3 sig figs. Most stoichiometry calculations require 4 sig figs. So 24.47. Is it 24.47? If you round it to 4 sig figs, I think. Is it 24.47?
For any gas, was that SUP?
Yeah.
24.47. All right. I put 24.5 on it.
So here, what we're going to do is this. You see the chemical reaction here is the mole ratio, not the mass ratio. And then Avogadro's law. Tell me what Avogadro's law says.
Avogadro's law says
The number of moles is proportional to the number of, or the
volume.
volume, milliliter. Oh, it doesn't matter. Milliliter is fine. In other words, the mole is directly proportional to the volume. And so when we have a balanced chemical equation, there are 2 ways of reading it. 1, the mole ratio. 2, the volume ratio. And the volume ratio, we come up with volume stoichiometry. As long as they're gases, they have to be gases. It can't be solids. It can't be liquids. And so with this, I can rewrite this as 2 liters of NO gas plus 2 liters of O2 gas gives me 2 liters of NO2 gas. And so the mole ratio is the same as the volume ratio, and I'll just pick easy volumes, liters, since I use liters all the time. Does that make sense?
Yeah.
And so this stoichiometry is very easy. But there's one restriction, and the restriction means that all these gases have to be at the same temperature and the same pressure. So if the NO were at normal room pressure, but the O2 was at high pressure, it doesn't add up because high pressure O2 has a lot more O2 in there, right? And so these have to be what we say at constant temperature and constant pressure. Then it works. This is why when we're doing we did an Avogadro's addition yesterday. We added O2 and air together. And the only way they can be combined linearly is if the pressures match. So we had to do all that pressure matching. Otherwise, we can't add it. Does that make sense? Yeah. And as we're out of time, so we'll just continue next.